it was meant to be done physically, but the situation is that we cannot travel and everything is closed down. So we'll have to do it like this. So the idea was at the beginning to have 3 hours more on theory and then to have a workshop, a separate workshop. And we have condensed everything into just 3 hours. So we will see a little bit of theory and a bit of how to compute these things using a computer program. And I will do a demo rather than a workshop where you are invited to, or where you have to make the calculations yourself. But if you have the programs in your computers, feel free to reproduce whatever I'm doing and asking whatever you have. And I'm not sure that I see the chat room. So if you have any question and I don't answer, just unmute yourself and make your question. So the slides I'm using are taken from a longer course that I give of 1 week of sample size calculation. So we don't have to see all of them, but just the main ideas. And you're free to take the full course and or to take the slides. The course is a CSIC one. So CSIC is the Spanish National Research Council. And yeah, so you have the slides, you have the book, everything is open, and you're free to ask me whenever you have any question. So let's start. You have already had some course or some lecture on experiment design, and I have seen the slides. They are pretty good, and I'm sure that you have had a broad idea of what the problem of experiment design is, how to organize groups, and how to compute or how to deal with factors in your experiment and so on. Today, what we'll see is sample size. So those are the two main pieces in the design of an experiment. So first, which are the factors and which is the layout of your experiment, and then how many samples you need for each one of the groups that you have in your experiment. And I would like to make you start the course with a question. And these questions are in Menti, so Rafael prepared some slides here. And so it is kind of survey. So I don't know if you have to do anything else. So you have to go to menti.com, and then there is a number that is this one, 664775. So 664775. You have to put it there, and then there should be a question appearing, but it doesn't appear. So I don't know if we need the help of Rafael for this or not. Rafael, do you know if?
Yes, I'm putting the web link and the code in the chat room, so everyone can click there and add the code. And I can see that 4 persons are already there, at least 5. So I will pass the questions. So
yeah, this one here. So the question is, a statistical calculation of the sample size implies that many animals, at least 30, are required by each group. So do you agree with that, disagree, or not sure about this statement? And after, once you reply, we will see a summary of these questions. So I'll give you a couple of minutes, few seconds actually, is enough.
I have hidden the results, but I can show the results later.
Yeah, sure. Okay, so what you will learn here is how to answer that question. So if we had to put a name to another name to these 3 hours, would be n equal whatever, and n is the number of sample of experimental units that you need for your experiment. And in the experiment design lecture, you had a long discussion of what an experimental unit is. But basically, it is the minimum amount of experimental material, and material could be animals, that you can change the treatment. So if you are given a control, you have two groups, control and treatment, and the control you are giving some vehicle with the not the drug, but just the same formulation for the drug, except the drug, and then the treatment with the drug. And so the experimental unit could be the animal. If you are feeding the animals and the treatment is put into the food, then all animals in the same cage would be the experimental unit. So you would have only one experimental unit per cage. And so n is the number of experimental units. And if you are very much interested in these things, either you can read my book now, or this one is also very good. It is rather technical, and unfortunately, it has a lot of equations that many people are a little bit reactive to them. But the problem is that sample size calculation requires equations. It is a calculation is something that you need to make some assumptions and compute how many animals you need based on these assumptions. So I try to simplify as much as I can the equations and give only the rationale behind the design concepts. Okay, so let's say that you are designing a new treatment and you want to see whether this treatment is useful, I don't know, to vaccinate animals or to treat animals for some disease or whatever. And the problem is how many mice or how many animals you need to put in each one of the groups to show that the new vaccine is effective. If you put too few, it is a waste of time and also a waste of money, because you are spoiling your experiment by just using very few animals. But it is also unethical. Unethical because you are doing something that is not good for the animals, and at the end, you will not be able to prove what you wanted to prove. And if you use too many, it is also a waste of money and a waste of time. And it is also unethical because you will prove what you want. If there is if really your vaccine is useful, you will be able to show it. But it is unethical because you could have done that with many less animals. So you just need enough animals. So not too few, not too many. And that is the objective of these equations. So giving you an idea of how many animals you need, and then allowing you to have more solid grounds to say my vaccine is useful because I have performed this experiment with this many animals. These many animals allowed me to show later in a confidence test that I have a significant effect on the vaccination state of the animals. So you may think of this sample size in this way. So here in green, I don't know if you see my cursor, but here in green you have the cost of the experiment. So the more animals you use, the higher the cost, and we can think of it in a linear way if you want. And here in blue is the cost of taking an incorrect decision. So let's say that you take very few animals, and in your very few animals, you are unlucky and you think that your vaccine is useful when actually it is not. So you take the decision to proceed to further experimentation, and this further experimentation costs money for something that is not useful. And that is a very costly decision. So, and the same happens if you are unlucky with your animals, you have very few animals, you are unlucky, and then your vaccine was useful, but just because of chance, your animals did not respond to your vaccine, so, or to your treatment. So taking the incorrect decision that this is not useful when it was, it is also very costly now in terms of cost of opportunity, but it is costly. So the more animals you have, the lower the probability that you take an incorrect decision. So if you use really, really many animals, like 100 animals, you are sure that what you see is the effect, the real effect of the, almost sure that you are seeing the real effect of your treatment. So there must be some optimum. And the optimum is somewhere in this region. So for this example that I gave. So in this region, so when we calculate the sample size, we are given kind of region where we should work. So in this example, we know that we cannot use 6 animals. We know that using 70 animals is just overkilling. And that is a kind of optimal somewhere between 20 and 30. So we will see later that sample size is not something that is really, really well determined. So we cannot say it is 23 and it is not 24, or it is not 22. So it is somewhere between 20 and 30, but it gives you an idea of how many you need. So when you approach statistics, many people have these unfounded fear. So they think that if they try to do a statistical design of the experiment, they will require, so the equations will tell you to use thousands of mice. This is not true, actually. So what happens is that there are 5 variables that are interrelated, and you fix 4 of them, and then automatically you can compute the last one. So these 5 variables are the relevance. This is the one that you are really interested in. So whether my vaccine is useful or not, whether my treatment is useful or not. And then there is another one that is the variance. The variance is what is the variability of the animals that I'm working with. So how do they respond to to the same level of my treatment? So I treat a number of animals with the same dose, let's say, and then what is the variability in the response? And then there are 2 technical variables that are the level of significance and the statistical power, that we will see later what they mean. And fixing these 4 variables, you can calculate the number of samples. But all these variables, they all participate into the same equation. So you could have, for instance, change the number of samples, the relevance. The variance is something that you cannot touch. It's something that is given by the animals and the experiment that you're doing. And the significance, then you would be changing the statistical power. So you fix 4, and the last one is automatically adjusted. So the number of animals that you need for an experiment depends on different things. The first one is some experimental constraints. So how the data is collected. For instance, you need you're performing an experiment where you need a minimum amount of material to do your measurements, or some mice die before you can measure, or you cannot handle more than 100 mice at a time, 100 or whatever number you want. Sometimes the mice move while you're injecting, so the treatment is not given so good. And yeah, all these constraints, you know them better than I do. But then there are also statistical constraints. And the statistical constraints are the ones that we will see today. And they refer more to how the data will be used. So the first one is how the data is collected. The second one, how the data is used. And then here you have questions like you will perform a comparison to a control group, or you will compare the mean of 2 groups, or the data is normally distributed, or this is the first experiment ever, so you don't know the variability at all, or whatever. And the final sample size is a combination of the two. So sometimes it happens that with your statistical constraints, the number of animals is something ridiculously low, like 2 animals, 3 animals, because you are looking for very big effects. So statistically, you don't need so many animals for that. But then with 2, 3 animals, you are not sure that those animals are can really represent the wide variety of animals in your population. So with just 2, 3, you prefer to make an experiment with a few more. So that really depends on your setup. So here is another question that I prepared for you. That is, maybe we can move to the next, Rafael. Yeah, so have you ever used a program to calculate the sample size of your animal study? And then here you're given 5 questions, 5 answers. Eventually, we will see all these results together. Okay, so as Rafael said, I'm part of the ethical committee, and then probably the legislation, the law there in your countries are similar. So before doing an experiment, you have to make an application describing your experiment, and part of the application is how many animals you will use, and you have to justify how many animals you will use. And typically, researchers fill this application by themselves, then they submit to the ethical committee, and the ethical committee evaluates it and then gives some feedback. And if the number of animals has not been correctly justified, then you are suggested to contact someone to help you with the calculation of the sample size. And then this is a very typical situation. The researcher comes back after being rejected by the ethical committee, and he starts the conversation like, I've been told that I have to talk to you to write in this form the number of mice for my experiment. I have enough with 3,000. This is a real example. So 3,000 is a lot of animals. And there is some justification for this 3,000, but let's see how the conversation goes. So what the researcher is really thinking is that I hate all this writing for the ethical approval of my experiment. All he wants is just to perform the experiment, and he doesn't know why he's talking to a statistician that knows nothing about his experiment, nor biology, nor chemistry, nor whatever. And then I reply, or the statistician would reply, okay, you may be right, you may be, maybe you need 3,000 animals, but maybe you need less, and then you are losing some of your time and some of your money, the funding that you have for your experiments in one experiment, that you could use these funds for some other experiments. And also you may save some mice lives. All these experiments that we do to animals, they are not really pleasant. So it is really unethical to do it on an unnecessarily high number of animals. Okay, so but you may also need more. And if you need more, then you are losing, it is not that you are losing some of your time, some of your money, some of the mice lives. It is that you are losing all your time, all your money, and all your mice lives for not having calculated how many animals you needed. And then you have spent all your grant on doing an experiment on which you will never show that your treatment is really effective. And this is really worrying. So this situation is bad, in which you need fewer animals. But if you need more animals, this is really, really bad, because you are spoiling completely your experiment. And all the tests that you will do later, all the p-values will not be low enough to show that you have a significant effect. Okay, so why don't you calculate how many animals you need? What you are doing? Okay, I'm studying how the area of a lesion changes with a new drug. Okay, so are there previous experiences? And this is a very typical answer. So of course, there is no previous experience. This is science. It's novel. It is the first time it is the first time in the world that anybody is doing this kind of experiment. Okay, so really, there is no previous experience. So you don't know if the lesion is of this area, 0.1 millimeters squared or 10,000 millimeters squared. So the lesion is around 50 millimeters squared. So there is already some previous knowledge. So it is true that probably this drug is the first time it is tested, but the kind of lesion, the kind of variability of the responses and all this, they are already known from similar experiments. So, okay, so if the lesion, if you don't do anything, is around 50, then you already know the mean of one of the groups. And we will call this group group A. So the mean of group A is 50. So when would you say your drug is interesting? I don't know. I just want to see what comes out from the experiment. And this question is actually asking for this variable here, the relevance. So what do you want to detect? So for instance, let's say that you have a new treatment that reduces the lesion from 50 to 49.5 millimeters squared. So would you say that that treatment is worth it? Would you do an experiment just to detect this small change? Probably not. Probably you want to see a decrease by at least 1/2. So the area of the lesion has to go down from 50 to 25. Okay, so this is the relevance. This is the effect size that you want to detect. So the difference between the control situation and what you would like to see. It doesn't mean that you will see that, but it means that with the sample size that you will calculate, if this happens, you will be able to show that it is statistically significant. If there is later when you do the experiment, if there is a bigger change, so you used more animals than needed, and if there is a smaller change, you have used fewer animals than needed to show that that there is a decrease. But you are interested in this kind of changes. If this change occurs, then with this number of samples, you will be able to see it. Okay, so now we know the relevance. The relevance is this effect size. So we want an effect size of 25 millimeters squared. Okay, so what kind of fluctuations do you expect around 50 in the control group? And in principle, you should also have it for the treatment. And for the treatment, it is true that it is the first time that you apply this treatment, but you may assume that has kind of similar variability. So what kind of fluctuations do you expect in each one of the groups? I don't know. The experiment is new. If it were not new, I would not have anything to publish. So again, it seems like a stupid question, but actually he knows more than he thinks. So for instance, let's say that we have two situations. So do you expect that in the control group, the lesions are something like 50, 49.96, 50.14? So all these numbers here are very close to 50. The average is 50, but they are very close to 50. Or you expect that the areas in the control group, they are more like these ones. So 58, 8, 31, 21. So the average is also 50, but they deviate a lot from 50. And statistically, you characterize that through the variance. So the variance of the first kind of measurements is 0.1, while the variance in the second one is 1000. So there are 4 orders of magnitude of difference between the two experiments. So detecting a change from 50 to 25 in the first group is extremely easy. With just one animal, you can see it. So if your treatment is so effective that it decreases from 50 to 25, in the first group, it is obvious. With just one animal, you can see it. But if you have the second situation, then showing that it decreases from 50 to 25 is more difficult. You see, in the control group, there are already animals that have less than 25. So there are like 8, 21. So it can be really tough to show that your treatment is effective if you have the second situation. It is tougher than in the first case. Okay, so what kind of variability you expect? And then if the researcher is stubborn, then he says, I don't have any clue. Okay, so if you don't have any clue about the variability, there is no other way than performing an exploratory experiment with a few animals. Then you see what kind of variability you have there, and then you repeat the experiment design with the variability that you have, because otherwise there is no way that you can say that you need 3,000 animals or 1 or 20 or whatever number of animals. If you don't have the variability of your responses, there is no way of calculating. And then he goes easier, and then well, there is a paper where they perform something similar to my experiment, but with a different drug. And for the control, they report the variance of about 1,000. So we would be more in this kind of situation where the average is 50, but there are already animals that have lesions that are smaller, much smaller than the target area that you have. So our target was 25, and there are animals below 25. And so the variance is 1,000, and for the treatment, it is less clear. We can assume that we have kind of similar fluctuations, but we don't know. Okay, so now you know the variance of the two groups, and the variance you can set them to the same value. Or if you are not sure about the treatment variance, you may increase it by some reasonable safety factors, so let's say 20–30%. And normally, for instance, if you are reducing the area of a lesion, or you are reducing your measurements, so your measurements goes down, typically the variability also goes down. But if your measurements goes up, for instance, you want to increase the level of, I don't know, the concentration of this particular metabolite in blood, and you want to increase it, typically the variability also increases. So it depends on which kind of experiment you are doing. You may have to decrease or increase the variability. And the safer, for instance, if you are your measurement goes down, then the safer is to keep the variability the same as in the control group. Probably it will be a little bit smaller, but it is true that you have not done the experiment, so you don't know. And then you keep it the same value. Okay, so let's say that in this case, we want to be a little bit safer, and we increase the variability by factor 20%. So now we increase the variability in one of the groups by 20% with respect to the other. So we have defined already these two variables, the relevance and the variance. And then there are these two technical variables. So these technical variables comes from the statistical test that you will do later. So in some cases, there is a difference between the treatment and so you're testing for differences between treatment and control. So let's say that there is no difference, but you are unlucky with your samples, and then you think that there is. a difference. And that is called a type 1 error in statistics. So there is no difference, but you think that there is. And you think because the p-value is below a certain threshold. And this threshold typically is chosen to be 5%. And so when you see all these publications that they have a confidence level of 95%, so what they mean is that in case that there is no difference between the control and treatment, I still have a 5% of probability of saying that there is, just because I was unlucky with my sample. So this 95% is widely accepted everywhere. Almost everyone is using 95%. There is nothing special, mathematically special about 95%, only tradition. So everyone is using in the biomedical sciences 95%. So there is no discussion typically about the significance. Then there is the power. The power is less now. So the power is just the opposite kind of error. So let's say that you have the treatment really makes a difference, but you are unlucky with your sample, and then in your sample you don't see this difference, and this is called a type 2 error. So you don't see this difference means that your p-value when you do the experiment will be above the 0.05 level. So it will be higher than the threshold on which you take the decision to say that there is a difference, and then you miss that true effect that the drug has. And normally, typical values for these are like 10% or 20%, and then the statistical power is just a complement of things. So if you use 10%, the statistical power would be 90. Or if you use 20%, the statistical power would be 80. And when you design an experiment, you should aim for high statistical power, because otherwise it doesn't make sense to do the experiment. Let's say that I do an experiment, but my type 2 error is 99%. So it would mean that in 99% of the experiments in which the drug makes a difference, I miss it. My p-values are relatively high, and then always I say that my drug is not useful. But actually, I'm probably with 99% of probability missing many drugs that are useful, and simply because I don't have enough power, I'm losing all these results. Okay, so let's say that you want to be sensitive, so you want a relatively low type 2 error. So let's say it is 10%. The more sensitive you want to be, the higher the sample size you need. Okay, so now we have all the variables. So we have the relevance, so what you want to detect. If this happens with this number of samples, I will be able to see it. The variability is something you cannot touch, but you need to know. You need to know how your animals respond more or less, at least to the control. And ideally, you should also know for the treatment. But if the treatment is new, probably you don't know with you're not very certain about what is the variability, but you can use estimates of what the variability should be more or less. And then now you have decided how often you want to be wrong. And with all this, you can already design the number of animals that you need in the control group, in the treatment group. There's a formula for that. The formula, this is the least complicated formula that you can have for sample size calculation. It is not complicated at all, but some people feel uneasy, and actually you don't have to. For instance, these T's here that they appear, they are the T students percentiles, and that you have to look them up in tables or use some function or whatever. But actually, you don't have to worry about this, because there are programs to do that. And I started this 10 years ago, and then at that time, I was giving them an Excel to do these calculations and a Word template so that they could fill the justification of the sample size. Actually, this sample size calculation that we have followed in this example, it is let's say 70% or 80% of the examples that of the experiments that we do. So normally you are comparing means of two groups, and you have always the control and the treatment group. So this is the most typical experiment design that we have, at least in biomedical sciences. Okay, so at that time that there was this this Excel. Now we will use a program for that, and we will repeat these calculations using a program. So good news, you don't need 3,000. You only need 31 mice in each one of the groups. Okay, but you know, sometimes mice get a cold, or they die, or they fight, or they do whatever that is not related at all to my experiment, but for this reason, or for any reason, they become useless for my measurements. So I cannot, because they have died from cold, let's say, then I cannot measure the lesion. And how often that happens? So let's say that it happens 20% of the time. So I lose 20% of the animals that I use for my experimentation. So instead of 31, you increase by 8. So you divide by 80% because you have lost 20%. So that when you compute the 80% of this new sample size, that is now 39, you still have the 31s that you needed for the statistical comparison. So you may increase the sample size from the statistical design. So the statistical design just tells you 31, but then from experimental constraints, you may increase it because you know that you are losing some of the animals and some of the measurements for whatever reason. And then you may also want to test several drugs. Actually, this was the hidden reason why he wanted to have 3,000. So when you make the application to the ethical committee, to the ethics committee, this procedure is supposed to be applied during, let's say, 3-4 years. So during these 3 or 4 years, you will not do a single experiment. You will test, let's say, 100 drugs during these 3 or 4 years, and then what you have to do is to replicate this design where you have 39 per group times the number of drugs that you want to test, and that is where the 3,000 is coming from. But if you start directly saying, I will use 3,000 without justifying how many animals you will use in each one of the groups, then it is a bad statistical design. Bad in the sense that, let's say that for traditional reasons, in your group, you always do your experiments with 10 animals per group. So 10 animals per group, in this example, would not allow you to tell whether the treatment is useful or not, whether there is this reduction from 50 to 25. And if you keep on doing experiments with 10 animals, no matter how many experiments you do, in most of them, you will not be able to show that there is this reduction that you wanted to show. So it doesn't matter if you use 3,000 animals in your whole life of the experiment, of the 3 or 4 years, that none of the experiments you do will be successful. And that is what we want to see from the ethics committee. So we want to see that you have thought about what you are doing, what you want to detect, what are the variability that you expect from your experiment. Maybe wrong or right at the design time. So you hope to do your best, but obviously there could be situations in which your estimate of the variability was completely wrong. Okay, bad luck. Try to do it better for the next time. But in general, you need to think about what is your situation and how many animals you need for a single experiment. And then you will replicate that experiment the number of times for the number of drugs that you want. Okay, so if you are testing several drugs, especially this applies when you are testing many of them at the same time. So there is an effect that is called the type 1 error inflation. So if you are doing, let's say that you are doing 100 experiments at the same time. So in these 100 experiments, if you choose your confidence level to be 95%, in each one of the experiments, you're pretty confident that what you are saying is relatively correct. So you have this 95% of chances of being, or 5% of chances of being wrong. But if you are doing 100 experiments, you are sure that on average, you will be wrong about 5 of them because of this 95. So you may want to reduce the alpha. Alpha is the type 1 error. So instead of having an alpha of 5%, if you are doing m experiments at the same time, you may want to have an alpha that is smaller. And this Bonferroni correction that you may have heard is the easiest one, and it is simply 5% divided by the number of experiments you are doing. So if you're doing 100 divided by 100, so your new type 1 error would be 5 times 10 to the power minus 3. So minus 4 actually. So what you want to keep is the alpha probability family-wise. So in this family of 100 comparisons, I want to have an alpha, a family error that is only 5%. Okay, so, and if you foresee that each one of the treatments might have a different design. So for instance, you're testing many drugs, but for some of the drugs, you expect that the variability could be smaller or could be higher. Then you would have to repeat this exercise of calculating the sample size for each one of the experiments. But if you foresee that more or less they all will be more or less similar, then you calculate once and then you apply always the same sample size. Okay, so what happens if I get an unreasonable number of mice? So let's say that I do my calculations and I need to use 300 animals per group, and 300 is a lot. I cannot afford to have 300 animals per group. So you have to relax something. So either you relax the significance or power, but these are things that normally people don't like to touch. So you don't want to make an experiment in which you have very high probability of being wrong about your statements. You cannot touch the variance because the variance is how the population of animals respond. So you cannot touch that. Or we will see later a little bit of how to reduce a bit the variance. And otherwise, what you can touch is the relevance. So if for detecting, if you need 300 animals, it's probably because you want to be very sensitive. So if in the example of the area of the lesion, so if you want to detect a change from 50 to 45, so just a 10% change, then probably you will need many more animals than if you want to see a very big change. So from 50 to almost disappearance of the lesion. So this almost disappearance is much easier to detect than just a small variation on the area of the lesion. So you have, that is the variable that you typically change. So I want to use fewer animals. I want to use just 10 because I cannot afford more than 10 per group. Then I know now that with 10 per group, I can, and this variance, what I can detect is this kind of effect size. So if I use just 10, I will be only able to show that there is a statistically significant change if the change is larger than the effect size that I use for this design. Then some people think that you should always repeat 3 times your experiment just to show that the result is significant. And this is not true. This depends, how many times you have to repeat your experiment depends actually on what is the p-value that you have. So the p-value is, let's say that you have a p-value that is very close to your threshold. So your threshold to take a decision of whether the treatment is useful or not is 5%. So this 0.05. If your p-value is below 0.05, you say the treatment is useful. If it is above 0.05, you say that you cannot show with this data that the treatment is useful. So let's say that your p-value is 0.049999. So it is so close to the threshold that if you repeat the experiment, it is very likely that you end up above the threshold, and then your treatment would not be significant. So actually, if the p-value is exactly at the threshold, then there is a 50% chance that if you repeat the experiment, you are in either side of the threshold. So there is 50% probability that you are above the threshold and 50% that you are below the threshold. So if your p-value is really, really low, so let's say that the p-value is 10 to the minus 6, no matter how many times you repeat the experiment, and you will always get the same result because it is so significant that it doesn't matter how many times you repeat the experiment. So actually, for instance, if the p-value is a 10th of the threshold, then there is an 80% probability of getting the same result if you replicate it. So the decision to replicate should be taken once you see the p-value. So if the p-value is close to the threshold, then you really may want to replicate the experiment. If it is well below the threshold, then there is no point in replicating it. Actually, it is much better to have larger sample sizes so that you have more statistical power and your p-values are lower than replicating the experiments. And that has been, now it is not so much in fashion, but like 5-6 years ago, there was a lot of papers complaining that many of the biomedical studies were not could not be replicated. So an independent lab could not have the same results as you had in your publication. And there were many reasons for that, but one of them was statistical, and it was having these p-values close to the threshold. So if your procedure is that you do an experiment, and then as long as you get a p-value that is smaller than the threshold, you write the paper. Then if your p-value was close to the threshold, it might be that you got this result just by chance. And then there is a real problem there. So there were many reasons for this lack of reproducibility of experiments, but one of them was certainly statistical. Okay, so summarizing the procedure. So you should first think of what you are looking for. So if you are looking for reductions in 25 millimeters squared in the area of your lesion, or what kind of effect you are looking for. And then you need to know what is the variability of your responses. So at least in the control. So in the control, things vary in this way. So to detect this effect size, I need this many animals. And so in this procedure, now you are kind of balancing your expectations about the experiment, the sensitivity that you want to achieve, the errors that you are able to admit. So how often you want to say that there is a difference when there is not, and how often you want to miss a difference that is really there. And then by adjusting all these variables, you can calculate your sample size. And in this way, you're guaranteed in the long term to save money from the grants, to save time, your time of doing the experiment, and most importantly, saving mice lives. That all these things are really, really bad to the animals. So
I have a question, sorry.
Sure.
So about the replicates.
Yeah.
Usually, so of course you will know the p-value at the end of the experiment, right?
Yeah.
So how can I make an estimate of the number of replicates? So the number of the experimental size, for example, when I'm doing an ethical permit application, if I don't know the p-value.
Yeah. So what you can write in the application is that depending on the p-value that you get on the experiment, you will take the decision to replicate it or not. And that is accepted. So all I want is to see that you have thought what you want to do.
Mm-hmm.
So you design your experiment, assuming that you have this variability, and then you calculate your sample size, and you may say, depending on the p-value that I get when I do the experiment, I will take the decision to replicate the experiment or not.
But that would make a huge difference in the number of animals, right? I mean, it can go to 1,000, from 1,000 to 2,000, let's say.
Yeah, yeah. If you are unlucky in all your tests, yes. But normally the way the applications work, you ask for 3,000 animals, and you hope that this will last for 3 years, let's say, that you will use 1,000 animals per year. And it might, you planned originally to test, let's say, 100 drugs, but then you have to replicate many of them. So it doesn't mean that you will increase the number of animals. It means that you will reduce the number of drugs that you will be able to test.
Okay.
So if you have to replicate all of them, so instead of having 100 drugs, I will test only 50. But this actually, it is good for your own interest. If all your p-values are so close to the threshold, normally you wouldn't want to publish something on which you could be wrong. So you want to replicate it. And if I have 1,000 animals per year, then instead of testing, I don't know, 20 drugs this year, I will only be able to test 10. But I want to be sure about what I'm saying.
Okay. Clear.
I have a comment here.
Yeah.
So for my experiment, what I did was I looked at the literature and then saw a similar experiment where they had done and used that p-value to calculate the power of my study. Is that okay? Is that reasonable to do?
So that p-value, so this is called post-hoc power calculation. So this post-hoc power calculation is another way of reporting the p-value. So there is a one-to-one relationship between p-value and the estimated power from once you have done your experiment. So it is not really a good practice. So the problem with that is that you're assuming that the effect size that you have observed is the true one, and that doesn't need to be true. So yeah, it is not really good practice, but it is a very widespread practice. So calculating this post-hoc power analysis. And yeah, I was to say something, but I forgot about that. Okay, any other question? No? So we can try to calculate these, to make these calculations, for instance, here in the program. So if you have G power, so you might calculate this thing. So G power is a free program that allows you to calculate sample sizes, and here you have different families. So actually, it is rather technical, or not rather, but the first question is very technical. So you need to know what you will do at the end. So for instance, let's say that we are comparing a control to a treatment group, and we are comparing the means. So you know that the test that you will do at the end is a student t-test. So you are doing a t-test, and then there are a number of experimental situations that the test at the end is a t-test. So for instance, the one that we have talked about is this difference between two independent means. So we have two groups, and we want to compare the means of the two groups. But there are many other that at the end, the test is also a t-test. So let's go for this one. And then we are given here another question. So compute the sample size given alpha, that is the statistical confidence, or 1 minus the statistical confidence, the power and the effect size. Actually, this is the one that we have been using for the design. But you see that you have all the other possibilities. So what is the required effect size given alpha, power, and sample size? So this is just the opposite that I told. So given that I will use only 10 animals, what is the effect size that I will be able to see with these 10 animals? And so this goes in the direction that I mentioned at the beginning. There are 5 variables. If you fix 4 of them, you can calculate the last one. And actually you have here 5 possibilities. So the one that we will use now is the required sample size. So there is another question, that is whether you will do a one-tail test or a two-tail test. So one-tail test is when you are interested only in changes in one direction. So in the example of the area of the lesion, you are interested only in drugs that decrease the area of the lesion. You are not interested in showing that this drug increases the lesion. So if it increases, I don't care. It might be that the drug is particularly harmful in that case, but I don't want to show that. So what I want to show is only when it decreases. So it is a one-tail test. And then you're asked for the effect size, and this effect size is a normalized effect size. So normally you want to calculate it, to use some kind of calculator to do that. So for instance, let's say that the mean of the control group is 50. I want to detect if it goes below 25. It doesn't mean that I will do the experiment and it will go below 25. But if it goes with this number of animals, I will be able to see it with this confidence and this power. And then you have to give the variability. So let's say that the variability is 10 in both groups. Probably in reality, the group with a smaller mean will also have a smaller variability, but just for the sake of calculation, let's keep it the same. And if you have a better estimate, then you can give, let's say that you know here the variability will be 6, so you put 6 there. But let's keep it the same. Now you calculate the effect size. So the effect size is in some way of normalization that we will do, we will see later. So this change of 25 in terms of standard deviations is 2.5, and we can see this easily. So in this example, this is the difference between the two groups is 25. 25 divided by 10 is this 2.5. So it is how large is what you want to detect in terms of standard deviations. How many standard deviations away you are from the control, what you want to detect. So what we want to detect in this case is 2.5 standard deviations away from the control. And then we can transfer this 2.5 to the main window. We can close this one. And then here you have the how often you want to be wrong about saying that the drug makes an effect, but it doesn't. So this is the type 1 error. This is the statistical power, and it has been fixed to 0.95, but you can put whatever number there. And whether you want to use the same number of animals in both groups or not. And then with these parameters, you need 4 animals per group. So it is relatively easy to detect something that is 2.5 standard deviations away. So let's say that we want now to we have much higher variability. So we have 5, 25, but the variability is much higher. So now the effect size is much smaller in terms of standard deviations, and it will be harder to detect. I need 26 animals per group. So the number of animals per group depends on how sensitive you want to be. So let's say that this 26 animals per group is not, it is a lot in your setup. So I cannot do an experiment with 26 per group. I can only do with 10, okay, or with 6. Many experiments are done with 6. So then, so what is the effect size if I use only 6 animals per group? So with 6 animals per group, what I'm able to detect are effect sizes that are 1.8 standard deviations away. So it doesn't mean, so from this sample size calculation, it doesn't mean that you have to do experiments with many animals, with fewer animals, or whatever. It means that fixing the sample size, you will be able to detect something. If that is what you are interested in, that's fine. And if that is not what you are interested in, you are spoiling your experiment. And many groups perform always the experiments with 6 animals per group, and this is fine. But they have to be aware that the kind of results, the effect sizes that they will be able to detect is only 1.8 standard deviations away, which is probably what they are interested in, but they were unaware, or they were unaware of that. They didn't know that they could see this. Any questions so far? No?
Sorry,
Then,
Carlos, is
sure.
this this program, is it for Mac also? I was finding it for.
I think it is for Mac and Windows. I'm not sure, but
Okay, you find it. Okay, I'll find it then.
I think it's for
yeah,
both.
if
yes.
you put G-Power
On the Mac.
software or something, and
Find it now.
you'll find it. So what I don't like from this program is that the first questions are kind of technical. So these F tests, people don't know normally if their test will be an F family test. And even they give you here some suggestions of what are the tests that at the end they calculate an F statistic. But yeah, this is not so easy. There is another program, we will see it later, that the questions are much more natural. Okay, so yeah, so let's continue a bit with this. So the thing that the sample size is based, the calculation of the sample size is based on how you will analyze the data. And that was the very first question of the program. So what you will do at the end? You will do a student t-test, then this is your sample size formula. And so let's see why it is that. So the first thing is, yeah, to decide whether you have a one-tail or a two-tail test. So a one-tail test is when you are interested only on one side of the reduction of the changes. So for instance, whether it reduces or it increases something. So let's say that you are researching on new vaccines and you want to show that the new vaccine reduces the number of infected animals in the population. So let's say that the standard infection rate is, I don't know, 5%, and you want to show that if you vaccinate your animals, your new infection rate is lower than 5%. So in H1, so in a confidence test, you always have, in a hypothesis test, you always have two opposing hypotheses. One is the null hypothesis, that is what you want to disprove, and the other one is the alternative, that is what you want to prove. So I want to prove that the new infection rate is smaller than some fixed number. So this is one tail. Also, I want to show that my new drug increases survival. So it increases survival, this is what I want to show. The survival rate is larger than some fixed number. Or for instance, let's say that you are producing some tablets and then you have to put the concentration of the drug on the tablets, and you want to stop the machine if to recalibrate it if the machine is malfunctioning. So if the concentration of the tablets is lower or higher than the prescribed concentration, then I should recalibrate the machine. So now I'm interested in changes in both directions. Either it is lower or it is higher, but I want to detect both situations. So what the nature of the alternative hypothesis is the one that determines whether you are doing a one-tail or a two-tail test. Then, yeah, I will skip some of these slides. This is for the longer course, but just for 3 hours, this is enough, I think. Okay, so there is something of a statistical inference that is not so natural. So it is that we can reject the null hypothesis and accept the alternative, we can fail to reject the null hypothesis because there is not sufficient evidence to reject it, but we can never accept the null hypothesis. And this is a bit like in legal trials. So in legal trials, the null hypothesis is the innocence of the defendant. So you can reject his innocence because I have so much evidence that goes against the assumption of innocence that I have to say that you are guilty. And there is always a certain risk. And this is the type 1 alpha, the type 1 error. That is, the null hypothesis was true, the defendant was innocent, but there was so much evidence against it that I made a mistake. So I can fail to reject his innocence. So I don't have enough evidence to show that you are guilty. So I can fail to reject your innocence. I fail to reject the null hypothesis. But I can never prove the innocence. So I cannot prove that the defendant is innocent, because for that I would need to know absolutely all facts. So for instance, if I'm measuring the reduction of the tension in hypertense patients, I would need to go to absolutely all hypertense patients in the world to show that the drug is effective. And I cannot do that. So I can fail. I can never accept the null hypothesis because I can never go to all the samples. So I can reject the null hypothesis. I can fail to reject it, but I cannot accept it. So what is the p-value? The p-value is the probability that if the null hypothesis is true, I observe a result that is as extreme as the one I have observed or more extreme than that. Okay, so let's see it with an example. Let's see it with an example. Yeah, I don't have it here. But for instance, let's say that you have a number of dices, having a result that is as extreme as this one, as having all 6, is really unlikely if the null hypothesis is true. So the null hypothesis is the dice is fair, so it is not biased towards 6, for instance. So having all 6s is really unlikely if the dice are not biased. So this is the p-value. P-value is if the null hypothesis is true, how likely it is to observe this result or something even more extreme than that. And we will see later another example that I think it will become more clear. So if the p-value is below our confidence level, then we reject the null hypothesis. So it is so unlikely that if, for instance, in the case of the legal trial, it is so unlikely that if you are innocent, all this evidence accumulates against you that I have to reject your innocence. So I have to reject the hypothesis that the vaccine does not reduce the number of infected animals, or that the drug does not increase the survival. So there is so much evidence that it is increasing the survival that I have to reject the null hypothesis. And that is the meaning of the p-value. Okay, so
Carlos,
yeah.
sorry, do you think we can have maybe 5 to 10 minutes break now? Is it a good time now to do it?
Sure.
Before we continue? I don't know if there's any question before we have a break from anyone. So if not, maybe it's now 10:20. Should we be back maybe 10:30, 10 minutes?
Okay.
We have some break.
Okay, good.
All right. Yes, thank you.
Thanks to you. I should observe a change in whatever concentration I'm measuring or whatever effect I'm measuring. So for 100 of these drugs, I should see a change. For 900 of them, I shouldn't. Then it comes these ideas of significance level and power. So let's see significance level. So with a significance level of 5%, that means that in 5% of the cases in which the drug doesn't make an effect, I see some effect just by being unlucky with my samples. So that means that in these 900, there are 45 that I declare to be useful, 45 drugs that I declare to be useful, and the rest, 855, I declare them not to be useful. So most of the not useful drugs I have correctly identified, but I have made a mistake with a few of them. And then it comes this statistical power. So statistical power is there is a true effect and I'm able to detect it. So for 80%, let's say that I have designed my number of samples such that I have a power of 80%. So in 80 of these 100 drugs, I will say that they make a difference. And for 20 of them, I miss them. And then I say that there is no difference when in reality there was. So now, reality you never know. So reality is something that God knows, but you don't. So what you know is the result of your test. So the result of your test, you have a positive result for this 80 here and for this 45. And from the statistical point of view, you cannot distinguish these two situations. So all you see is that there are 125 tests that said that the drug made an effect. But actually, 45 of them were false positives. So false positives, positive because you said that there was a difference, and it is false because there wasn't. So the positive rate, the false positive rate is 45 divided by 125. So it is much higher, it is 36%. It is much higher than the 5% that you aimed at the beginning. And this is where the Bonferroni correction comes in. So the family false positive rate of this 1,000 tests is 36%. It is not 5%. So you're committing many more mistakes than you expected at the beginning. And this is something that we are not aware when we are doing tests. Maybe you are not doing 1,000 tests at a time, and then probably you become conscious about this problem. But if you are doing experiments over 10 years, you have done many tests. And the false positive rate of your test is much higher than the 5% that you expected at the beginning. And that was another part of this lack of reproducibility that as a field of biomedical sciences we have been blamed for. So the significant test that the significance level that we have chosen, this 5%, is such that 1 in every 20 experiments you will declare that there is a difference when actually there is not. And there has been suggestions to decrease this significant level. We said at the beginning there is nothing special about 95%, only tradition. So by tradition, we could change this tradition to be 99%, for instance. And I don't know if you were aware of this problem. And we prepared one of the questions. So next question, for instance, in the Mentimeter, Rafael, if you can go to the next one. The next one is, after this reasoning of having a much higher false positive rate, do you feel concerned about your positive results? I would, but it is just a joke. Okay, so now statistical inference, because later the sample size will be calculated based on how you will analyze the data. So you need to know how you will analyze the data for calculating how many samples you need to show what you want to show. Okay, so let's say that you're an engineer, you're working for a pharmaceutical company, and you are in charge of the machine that puts the drug into the tablets. And you know that you should put a target amount of 250 milligrams, and the manufacturing process has a standard deviation of 1 milligram. This is just to put this in numbers. And then every month, let's say that you take 20 tablets, you measure the average amount of drug in the tablet, and you observe 250.66 milligrams. So then you wonder, okay, so this 0.66 is away from 250. So there is a small deviation. Is it possible that the machine is malfunctioning, or it is correctly working, and then I should leave the machine alone? So both decisions have economical impact. For instance, let's say that the machine is correctly functioning, I stop it for calibration, and then I'm stopping the production of my company, and that is very costly. But on the other side, if the machine is malfunctioning and I don't stop it and I get an inspection, I would get a high fine for not putting the right, for not keeping the quality of my production. So what I want to show is that the machine is malfunctioning. So what I want to prove is the alternative. Remind that you can never prove that the machine is correctly functioning. For that, you would have to see all the tablets forever from this machine. So we want to disprove the null hypothesis, and we want to show that the machine is deviated either above or either below the specified concentration. So let's see how the data is collected. So let's say that I observe a single tablet. So from a single tablet, in blue here we have the distribution of tablets in general. So I would expect that they are manufactured with a mean of 250, and they have a standard deviation of 1 milligram. So that means for the Gaussian, that means that almost it is 99.7% of the Gaussian is between the mean minus 3 sigma and the mean plus 3 sigma. So between sigma is 1, so between 247 and 253, I should see most of my tablets. So I take just one tablet, and it gives a value of 250.5. So with just one tablet, what is my estimate of the current state of the machine? So all I can say is that my estimated mean, so the hat here means estimated. So my estimated mean is the tablet that I have seen, because I don't have any other evidence. So at this moment, what I have to say is that my mean, my estimated mean has this 250.5 as average, and the uncertainty about the mean. So how sure you are that the mean is that one is you cannot be very sure. You will have the same uncertainty as you had for a single tablet. So for a single tablet, you have a sigma of 1. So for the mean, for your estimate of the mean with just one tablet, you will also have an uncertainty of 1. So with just one tablet, you think that the true mean must be somewhere below this curve, the black one. Okay, so now we have 2 tablets. So with the second tablet is, let's say, 251.7. So now my estimate about the mean, my estimate of the mean could be a little bit better, because I can take the 2 tablets that I know, the 250.5 and the 251.7, divide by 2, and that would be an estimate. And if everything goes fine, so if the machine goes fine, the expected value of this estimate should be the true mean, so it should be 250. And the variability or the uncertainty that I have around this mean, now it is a little bit reduced, because I have 2 tablets instead of 1. So it is the uncertainty that I had for 1 tablet, that was sigma squared, but now divided by 2 because I have 2 tablets. So I have a little bit less uncertainty about what is the mean of my machine. But now I have a third tablet. So with my third tablet is here in 247 whatever. And now my estimate of the mean is the average of the 3 values. And the average now is almost 250. So if now I have an inspection, I'm perfectly fine. I don't have many tablets, but I'm perfectly fine. The average is 250. And I have a little bit less uncertainty. So you keep adding more and more observations. And the more observations you add, the less uncertainty you have about what is the average, the true average. So after 20 tablets, this is the situation. So here we have the 20 bars corresponding to the 20 tablets, and the mean is 250.6. But if we observe about how sure you are about that mean, 250 is very far away from the mean you have observed. So it would mean that if the machine is correctly functioning, it is really, really unlikely that you observe a value as large as 250.6. So 250.6, even if the deviation is only 0.6 milligrams, with 20 tablets, I have enough power to say that, I have enough evidence to say that the machine is not correctly working, because it would be very unlikely that we observe such a high mean if the machine is really working correctly. And I have very few uncertainty about that statement, because my uncertainty about the mean of the machine is the uncertainty of each one of the tablets, but now divided by 20. And if instead of 20 I have 100, I don't have any uncertainty at all. So the machine is incorrectly working. So I should stop it and recalibrate it. Okay, so the first step is you define your hypothesis. Then you need to know how the data is collected. What are the implications of this hypothesis? A part of the hypothesis was that the data was normally distributed with this mean 250 and this standard deviation under the null hypothesis. So you need to say, if the null hypothesis is true, then I should expect this distribution from my measurements. Then the second step is to find a statistic. A statistic is a small calculation that you know how it is distributed. So if the tablets are normally distributed with this mean and this variance, then my estimate of the mean is distributed with this mean and this variance. And if this is Gaussian, this is also Gaussian. And then if this distribution of the, if this estimate of the mean is distributed like this, then this calculation that I will do, so this is the estimate of that I have, or the mean that I have observed in my 20 tablets. This is what it should do, what it should be, and this is the uncertainty that I have about that mean. So this small calculation should be distributed as a normal 0, 1. So now I do my experiment and I plug in my data. So my data says you have observed 250.66 as the mean, as the average. It should be 250, and this is the uncertainty that you have. So the set is 2.97. Now you go to the set should be distributed as a normal 0, 1. So now I have to calculate the p-value. The p-value is, what is the probability of observing 2.97, a result that is at least as extreme as 2.97. So you go to the normal 0, 1. So the normal 0, 1 goes from -3 to 3, and then observing 2.97 or more extreme than that. And more extreme than that is only this area. So the area under the Gaussian gives you the probability. So it is only this area, but it is as extreme observing a positive deviation of 0.6 or a negative deviation of 0.6. So if the machine is correctly working, positive deviations of 0.6 should be as extreme as negative deviations of 0.6. And this is where the two tails comes in. So you have to look at the probability on both sides of the distribution, that is the two tails. And when you are doing a one-tail test, you are only looking for the probabilities on one side of the distribution. So these areas is only 0.003. So that is, if the null hypothesis is true, only in 0.3% of the cases of my experiments where I take 20 tablets and I compute the average, I would observe deviations that are as large as 0.6 milligrams. So now it is where the threshold comes in. So this threshold of the confidence level was 0.05. If your p-value is smaller than that, then you reject the null hypothesis. There is so much evidence, and so much evidence is so many tablets whose average is this one, that I have to reject the null hypothesis that the machine is working correctly, because if the machine was working correctly, only in 0.3% of the experiments in which I take 20 tablets and compute the average, only in 0.3% of them, the deviation is as large as 0.6 or more. And then we put the stars on this p-value. So typically the stars that we use in biomedicine are these ones. So if it is below 0.05, you put 1 star, or below 0.01, 2 stars, and so on. Okay, so we get 2 stars for this result. And then let's see the connection of this process to sample size. So let's summarize it again. So you define your null hypothesis. The null hypothesis is that the machine is working correctly. So it has 250 as the mean, and the data is Gaussianly distributed. Then if this is true, I know that set, that is this small calculation, is distributed as a normal 0, 1. Then I do the experiment and I plug in my data. And for my data, I get 2.97. Then you will calculate the p-value with the area of the two tails. And you will decide that you will decide to reject the null hypothesis because it is below some threshold. Okay, so now this is when you perform the experiment. But before doing the experiment, since I know how you will process the data, I can try to determine what is the sample size. Okay, so let's say that I fix what do I want to detect. So I want to detect deviations that are at least as large as 0.5 milligrams. If it deviates more than 0.5 milligrams, I want to see it. Then the population variance is what it is. So this is how the tablets are deviate from the mean. And then I know that you will reject your null hypothesis if the p-value is below 0.05. So what is the threshold? So what is the set such that this area that we have plotted in blue, that for this example was 0.003. So what is the set for which that blue area is 0.05? And that set is 1.96. So for 1.96, the area in the two tails is 0.05. And I know that if your area is below this 0.05, you will reject the null hypothesis. So to design the sample size, what I can do is, okay, let's look at the set again. So the set is the difference between your observed value and what was specified. So that is the difference. That is the difference, the deviation between your observed value and the specified value. So this is the 0.5 milligrams that we fixed at the beginning. And the rest of the formula is known. So this is what I want to detect, delta is what I want to detect, sigma is the deviation of the tablets, and n is what I want to calculate. So I know that you will reject set, you will reject the null hypothesis if set is beyond 1.96. So now I have an equation that allows me to calculate n. So I know delta because I have fixed it. I know sigma because I have seen many tablets in the past. And then I can calculate n. And n in this case is 15, 15.4. So you cannot take 15.4 tablets. So either you take 15 or you take 16. And you always have to round up, because if you round down, you're losing some confidence. So you always round up. So we will take 16 tablets. And with our 20 tablets, we were on the safe side. So we were taking a few more than what's needed to detect these deviations of 0.5 milligrams. So let's analyze the formula again. So the formula is the number of samples is something that is related to the confidence. So this 1.96 came from the 5% confidence, and something that depends on the variability of your observations, that is sigma, and what you want to detect, that is delta. So here we have the formula, and then let's see if it goes in the right directions. So let's say that I want to be more confident. So if I want to be more confident, that means that these blue areas have to be smaller. And if the blue areas are smaller, then the set has to be larger. So instead of 1.96, I will have some larger value. So if you want to be more confident, then Z will increase, and if Z increase, N will increase, and it will increase quadratically. So that means you want to be more confident about stopping the machine. So not so you want, let's say that I use a 5% confidence. So on average, if I do this test every week, so every 20 weeks, one of them, the machine is working correctly, but on average, one of them, I will say it is not working correctly. So I will stop the machine on average once every 20 weeks, even if it is working correctly. So if I want to be more sure about stopping the machine, I have to increase my confidence level, and then I will need more than 16 tablets. I will need, I don't know, 30 to be more sure. Then the sample variance. So if my data, instead of changing, if my observations, instead of having a standard deviation of 1, has a standard deviation of 2, then it will be more difficult to detect these small changes of 0.5 milligrams. So if the standard deviation increases, also the number of samples should increase. And then it comes the sensitivity. So the sensitivity is how fine you want to, how sensitive you want to be. So if you want to detect changes of 0.5 milligrams, you need 16 samples. If you want to detect changes of 0.05 milligrams, you need many more samples. And then it comes a technical question again, that is whether you are using a one-tail or two-tail test. And the thing is that if you use a one-tail test, instead of having here this number is 1 minus alpha half. So alpha half comes from the fact that, let's say that you have alpha that is 0.05. So the area from minus infinity to 1.96, that is somewhere here, is such that the remaining area is alpha half. So this is this notation. So this notation tells what is the set such that the area up to that set is 1 minus alpha half, and the remaining is alpha half. So if instead of making a two-sided test, you have a one-sided test, a one-tail test, then the area, the set that you need to use is set 1 minus alpha. So 1 minus alpha will be a little bit to the left, this one. So 1.96 is such that this area on the right is 2.5%. If we are doing a one-tail test, the area to the right is 5%. So we have to move the 1.96 a little bit to the left. So making one-tail tests is a little bit cheaper than in terms of samples than two-sided tests. And we can think of that in the following way: the more information you add to the system, the easier it will be to show the effect that you are interested in. So let's say that as an engineer in this company, you have always observed that if the machine malfunctions, it always decreases the number, the amount of drug in the tablets. So you are only interested in showing that part, because you know that it never goes up. If anything, it goes down. So you are adding some a priori knowledge, and this a priori knowledge translates into a one-tail test and then into a lower number of samples. And this also applies to our research. So if I'm only interested on one side of the comparison, so let's say that I have a new vaccine, I'm only interested in showing that the new vaccine is effective to prevent infection. I don't want to show that the new vaccine promotes infection, even if it could. I don't know if that could be the case, but even if my substance could increase the infection rate, I'm not interested in showing that. So I'm adding the a priori information that I'm only interested on one side of the comparison. And then I will need fewer samples. This is very important because when you do an experiment with animals, if you could add this extra a priori knowledge that you are interested only on one side of the comparison, the number of animals that you will need will be smaller. But then in this whole story, the statistical power is missing. So let's complete the story. Let's tell you the full story. So here what we have in this plot is the distribution that you would expect of the average, of the observed average, if you have 20 tablets. So if you have 20 tablets and the machine is working correctly, then you should see the blue curve. So the mean should be 250, but with 20 tablets, you could see deviations that go up to minus 0.5 plus 0.5 milligrams. So if everything goes fine, if the machine is working correctly, observing a value of 249.8, so somewhere here, would not be very unlikely. So it would be a normal result. If I see 250.6, this 250.6 is rather unlikely if the null hypothesis is true. That is why I reject the null hypothesis. But let's say now that the true state of affairs is that the true mean is really 250.6. So then this would be the normal values, the standard values that I should see from my experiment. So observing 250.6 would be the most likely result, but observing 251 would not be very unlikely, and observing 250 is very rare. So let's go back to the null hypothesis. So yeah, you have a question? No. Okay, so let's go back to the null hypothesis. So when I collect the data, I will reject the null hypothesis if the set goes beyond 1.96. So I could translate this 1.96, this is set here, I don't know if you see my cursor, but this set 1 minus alpha half is the 1.96. So if the mean that I observe is beyond this point, this specified concentration, that is 250, plus 1.96 times my uncertainty, and that is this red line. So if it goes beyond that point, I will reject the null hypothesis. So how likely it is that if the true state of affairs is the black curve, how likely it is that I cannot reject the null hypothesis, so that I'm on the left side of this red line. So the probability of being in that situation is all this area. So all the area of the black curve on the left side of the red line. So now I can expand my equations to say all this area at most has to be 20% or has to be 10%. That is what we fixed when we were using the G power. We said my statistical power has to be 90%. So 90% should be the area on the right. And then the area on the left is 10%. So now we have the full picture here. So you have the null hypothesis. If your observed set is beyond some threshold, you will reject the null hypothesis. So this area on the red line to the right is is related to the type 1 error, while the area from the black curve to the right of this red line is the type 2 error. And then I can write an equation in which I know everything except the n, and then this n is something related to the confidence level, is something related to the statistical power, to the variability of my observations, and to the effect size that I want to detect. So now, yeah, and I have explained it with positive deviations. So the black curve is on the right, but we could make the similar reasoning with the negative deviations, and then the black curve would be on the left, and we can have both together. And interestingly, the equation, whether it is on the right or on the left, it is the same, because the Gaussian is symmetric. So it doesn't matter if the deviation is positive or negative. So now let's go to this slide. So in this slide we have the sample size equation for the Gaussian, and what we have is something related to the confidence, something related to the power, something related to the variability. If I want to have more confidence, more power, or my observations are more variable, I will need more samples. On the other side, if I want to be more sensitive, delta will go down and then n will go up. So if you want to be more sensitive, more samples. If you want to have more confidence or more power, more samples. If your observations are more variable, you need more samples. And then there is this technical question of whether you are doing one or two-sided tests. And if you are using two-sided tests, then you need more samples, because you are adding less information, a priori information, into the system. So, any questions so far?
No.
We're fine.
Okay, good. Okay, so let's think a bit about variance.
There's a question in the audience. Raul, do you have a question?
Yes, I actually did, but I was struggling with the buttons a little bit. Sorry. I'm still thinking a little bit about this one-sided testing. I dropped a chat on that.
Yeah.
In effect, in some of the examples you gave, for example, the vaccine, it does actually occur that vaccines after infection promote disease. So this could be viable in valid information to get from your experiment. If you a priori exclude that, then you would perhaps, create the possibility that you miss that your treatment might be actually worse. And if you don't do that properly, then I'm afraid that you're basically just increasing your alpha, sort of sneaking and doubling your 0.05, for example, to a 0.1. Mm-hmm. I'm worried that if you design an animal experiment where you sometimes do not really expect, so you can't really predict what's going to happen in biology. For example, wound healing might also be different. We discussed that quickly. I'm worried that you might be missing out on information that you did not necessarily expect.
Yeah.
So I would really be cautious about using this one-sided testing.
Yeah, yeah. So let me rephrase it in different ways. So let's talk, for instance, about wound healing. So wound healing, I could give you a drug or a treatment, and this treatment could actually slow down the pace of the healing. But I'm not interested in these treatments. I'm only interested in treatments that accelerate the healing. So let's say that I'm interested in drugs or treatments that accelerate. Then I need, let's say, 20 animals. But I'm interested in characterizing a treatment. So in characterizing a treatment, then I want to say this treatment accelerates or slows down the healing.
Yes,
and
thank
then
you
I
very
will
much.
need more animals.
I very much agree, and thank you for the comment. The point that I also wanted to raise here is that this is a very important decision that you have to make. It's really the design of the experiment will be for, as you say, characterizing versus like checking only the effect that you're after. And your previous example where you had the picture of this student or scientist that is discussing with the statistician, he says, yeah, at some point, I'm just interested to see if something happens. And I just wanted to make sure that it's clear that in that case, you can't do this.
Yeah, exactly.
Yeah.
Exactly.
Thanks. Don't let me stop you more.
No, it's fine. I think it is better if we discuss whatever. Yeah, it's more interesting. Okay, so any other question? No? Okay, so let's think a bit about the variability. So the variability, there are two variabilities here. So one is the variability of my observations, that they are what they are. And another one is my uncertainty. So variability and uncertainty is almost the same thing. So the other one is the uncertainty that I have about the mean. So for instance, in this example of the tablets, the more tablets I add to the experiment, the less uncertain I will be about what is the mean of those tablets. So the tablets don't change. The tablets are still as variable as they were, but my uncertainty about the mean is different. The more tablets I have, the less uncertain I will be. And this is the same with animals. So the animals are as variable as they are, but then my uncertainty about what is the mean of the effect of this treatment will be smaller and smaller the more animals I add. Then let's say that I have so my observations have some variability. Can I reduce a bit the variability of my observations? So let's think of the process of measuring, for instance, blood pressure. So my observation is the blood pressure observation. So for any particular individual, let's say individual I, it has a particular blood pressure, and I want to measure it. But every time I try to measure, I commit an error. And then this error will also go into my observation. So what I observe is the actual blood pressure plus my measurement error. So the variability of my observations is the variability of the blood pressure between people. If I measure different individuals, I will observe different blood pressures. So I have a variability due to the inter-individual variability, but I will also have a variability coming from my observations, from my measurement process. And the total variability that I observe is the inter-individual variability, plus, if you want, the intra-individual variability due to my measurement process. So let's say that instead of measuring the blood pressure once, I measure the blood pressure a few times. And then I average all my observations. So every measurement that I do, let's say that I take M measurements of the same individual. So every observation will have the true blood pressure plus a random number that comes from my measurement error. And the true blood pressure goes out, and then the average of I'm computing actually the average of the observation errors. So by adding many observations, I can make this average to go to 0. And actually, that is translated in terms of variance, the variance of my new observations, but now my observations is the averages of my M observations. So I measure the blood pressure 10 times, and then my estimate for a particular individual is the average of these 10 measurements. So the variability of my new measurements, that are the averages, is the variability between people plus the variability of my observations, but now divided by the number of observations, by the number of times I compute the average. So I can reduce actually the variability of my observations. And the same happens with, this we can skip. The same happens with factors. So when you, for instance, you are measuring blood pressure. So blood pressure has men and women, they have different blood pressures. So part of the variability is caused by the gender of the person I'm measuring. And then the variability of my observations, I can decompose it as a part that is explained by the gender, a part that is explained by the treatment. This is actually what I'm interested in. If I give you this treatment, I lower blood pressure, and then this lowering is a variability. So this is what I want to detect. And then I have the variability of the people and the variability of my observations. And by controlling the factors, so if I do an experiment in which I have male and female individuals all together in the control and all together in the treatment, and I don't distinguish them, for me, they're all the same. So I cannot estimate what is the variability induced by the gender. But if I separate them in the control, and then I annotate this is a male, this is a female, this is, and in the same for the treatments, then I can estimate what is the variability caused by the sex. And when I want to show what is the effect of my treatment, actually I have to compare the variability caused by my treatment, that is the decrease that I want to observe, compared to the variability that I cannot explain. So if I can explain a part of the variability of my observations, so my observations will have sigma squared, but that sigma squared can be explained partly because of the gender, partly because of the biological variability, partly because of my observation errors, and partly because of my treatment. And you have to compare the variability caused by your treatment to the variability you cannot explain. And if you can, if a big part of the variability is explained by the gender, then it will be easier to say, to show that your treatment is effective. And actually, this idea is the one behind ANOVA. So ANOVA is called analysis of variance. In the analysis of variance, I want to show that the treatment makes an effect. But to do that, what I show is the variability, is that the variability caused by my treatment is significantly higher than the variability that I cannot explain. So that is why in the experimental design lecture, you were thinking about all the factors and how to organize these things in the individuals in different groups, different factors, and so on. Because by that organization, you will be able to identify what is the variability caused by the gender, what is the variability caused by the experimenter, what is the variability caused by whatever other reason, and whatever is left is what determines the level of noise. Actually, if we look at this formula here, the sample size has confidence and power, that's fine, but then it has the effect size and the noise. So sigma is the variability of my observations, that is noise, and the effect size is what I want to detect, that is the signal. So actually this is a signal, this is the inverse of the signal to noise ratio. So when I identify, when I do an ANOVA test, what I'm trying is to show that the treatment is well above the level of noise. And the level of noise is whatever you cannot explain. So in this example here, I cannot explain the variability between people because I have not measured any genetic thing or whatever. So I cannot explain the variability between people. I cannot explain my measurement errors, but I can explain the variability caused by the gender. So by identifying factors and blocking those factors, and blocking is something that you saw in the experiment design lecture, you can actually reduce the number of samples that you need, because the sigma that you need to use in this formula is the sigma that you cannot explain. So is only the part that you cannot explain. And then at this point, I thought of making another question. And this is a really interesting question for you. That is, we can go to the next one, Rafael. That is, if you can think of ways to reduce the variability in your current experiments. And this is really a good exercise for you to think, I can measure more an average, or I can use another variable that is related to what I'm looking at. For instance, let's say that I give a treatment and then I can measure the concentration of metabolite 1, metabolite 2, metabolite 3, but the variability of metabolite 3 is much smaller than the variability of metabolite 1. So I could concentrate on metabolite 3 to show that my drug has an effect. Or, for instance, I could block these variables that affect my experiment. I can explain what is the variability caused by these variables, and then it will be easier to show that my treatment is effective. So I'll give you a couple of minutes, 2-3 minutes, to think of different ways of reducing the variability. Okay, so let's come back. We will see all these questions and answers at the end. Okay, so I think this is a good overview, some very simple overview of the sample size. And let's see some other ideas about sample size. So I do my sample size calculation, I get a number. When is this number completely wrong? So the most important reason is when the sample variance that I use to calculate the sample size is wrong. So we tend to be over-optimistic about the variability of our samples. So when we design an experiment, we tend to think that the observations that we will have vary much less than reality. And then if you are wrong by a big, large error, then your sample size that you have calculated will be completely wrong. And you have seen in this very simple example, the sample size depends quadratically on the sample variance, so on the standard deviation. So if the standard deviation has you make an error by a factor 2, then the sample size will be wrong by a factor 4. Then the distribution of the samples does not follow the hypothesis. So we started all our design saying our samples are Gaussian. If our samples are not Gaussian, then the calculations are not correct. Or, for instance, we assume the two populations to have the same variance and they don't have the same variance, or we assume the two populations to have the same distribution when they don't. So the part of the null hypothesis, let's say that under the null hypothesis, things are Gaussian, but under the alternative hypothesis, the observations are not Gaussian. Then the sample size equation would be different in that case, and the one you have used, assuming Gaussianity on both sides, is not correct. How incorrect is incorrect depends on the violation, on the amount of violation you have incurred. Then sometimes we transform the variables to analyze them. So, for instance, it is very typical if you have concentrations or titers of virus or number of cells or things like that, that you take the logarithm. And the logarithm is meant to make the observation Gaussian. Sometimes the transformation that you do doesn't fully conform the Gaussianity. And then the sample size that you have used would be incorrect. Then what to do if the sample size is too large? Then you have to change something, and something you can change is to reduce the variability of your observation. So if you can improve somehow the repeatability and reproducibility of your observations, then you will reduce the variance and you will have a lower sample size. If you can introduce blocking variables like the sex in the example of the blood pressure, you will also decrease the variability, and then you will decrease the sample size. If you can use a variable with better precision, in my example of metabolite 3 having less variability than metabolites 1 and 2, then you will also decrease the sample size. If you can use more informative variables, so a continuous variable, that is normally the ones that we have in biomedical research, like what is the average of whatever. So that is the most informative variable, but there are other variables like is this feature present, yes or no. So yes or no is a categorical variable, and it has much less information than a continuous one. For instance, you could say, are macrophages present in my histological tissue? So yes or no, or how many are there, and how many are there in my field of view has more information than yes or no. And also, if you can identify covariates. So let's say that your experiment may depend on the room temperature. So you can decompose in this decomposition that I did of the variability, you can include room temperature as part of the explanation of the variability. That there are statistical ways of doing that, and there are equations for that. So if you can measure the room temperature, is the same as you are measuring the gender of your observations, or you are adding information into the system. The more information you add into the system, the more you will be able to explain, and then the less unexplained variability will remain, and the easier it will be to show that if the treatment has an effect. And another possibility is this one of using paired samples. So paired samples, let's say paired sample is when, well, this is one of the examples, when an individual acts as its own control. So let's say that you measure the blood pressure before the treatment, then you give the treatment, and then you measure the blood pressure after the treatment. So the true observation is the difference between the after measurements and the before measurement. And in that way, you are getting rid of the variability in the inter-individual variability, because now your observation is referred to the same individual. So this term of inter-individual variability would go away. And these paired samples is a very powerful way of having a low number of animals. And with animals, for instance, depends on the treatment and what you are studying. But for instance, they have two legs, so you can apply one treatment to one of the legs and the other treatment to the other leg. Or they have two eyes, so if you are looking into eye drops, for instance, you can apply an eye drop into one eye and another eye drop onto the other eye. So every time that you can have paired samples, you will reduce the number of samples very much, because you are reducing the variability of your observations. Then it comes this idea that sometimes you are using non-parametric tests to analyze the data. So we started all our sample size design saying, I need to know how you will analyze the data. And we made, in the example of the concentration of the drug in the manufacturing machine, we made a set test, hypothesis test. But sometimes you know that your data is not Gaussian, so you will have to do a non-parametric test. There are no formulas for sample size calculations for non-parametric tests. And there is a substitute that is you do the sample size calculation for the corresponding parametric test. For instance, let's say that you're comparing the mean between two groups. So the t-test would be the normal test for Gaussian data, but for non-parametric, for non-Gaussian data, you would do one of the Mann-Whitney U-test or Wilcoxon rank sum test. So you take the equivalent, the Gaussian equivalent, that is the t-test. So you calculate the n, the number of samples that you need for that test, and then you correct for it, for the fact that it is non-parametric. So these corrections, this is called the asymptotic relative efficiency. So this is a number that is smaller than 1. So smaller than 1 means that the number of samples for the non-parametric test will be a little bit higher than for the parametric, the corresponding parametric test. And it makes sense with respect to what we were saying before, that the more information that I add into the system, the fewer number of samples I will need. And into a parametric test, you are adding more information because you are saying that the data is Gaussian. If you don't have that information available, then the non-parametric test will need more samples to be able to show the same as the parametric test. And here is another interesting idea about reduction of the number of animals. So by using a non-parametric test where you shouldn't, because the data is really Gaussian, you are either decreasing your power or using more animals than needed. So if the data is really Gaussian, there is no point in using non-parametric tests because you are losing part of your information, and either you're using power to show an effect, or you need more animals to show the effect size that you are interested in. Then, yeah, so we will skip all these. And I would like to show you in the last minutes that we have another program that is PASS. So this PASS is another sample size program, sample size calculation. And I think that the questions that it makes are more natural than the ones that of G-power. So it organizes, it is much richer than G-power. So in PASS you have like 1,000 different designs, and some of them are really specific, like designs for microarray data. So this is really specific. But it starts asking, what are you looking at? So I'm looking at means. So if you are looking at means, the means of what? So I will look at means using ANOVA, or I will look at the mean of one group, or the mean of paired groups, or two independent means, or there are many possibilities. And for each one of these possibilities, it asks now what kind of test you will do, how you will analyze your data. So you will do a t-test, or a set test, or a non-parametric test, or whatever. And then I find this more natural. I think that the organization, I think it is closer to the way researchers think. And for instance, we can do a t-test in which we can have the same variance, or and we want to enter the mean. So the means is the 50 and 25 that I was giving at the beginning, or we have two groups, but I want to enter the difference, so the effect size, or we have an equal variance, and all these questions are related to, for instance, here it is very easily shown. So the t-test we had before, say the difference between two groups, we had the values here. So the design principles are always the same. So we have a distribution of the statistic depending on which comparison you are doing at the end. So we are doing a t-test. So for the t-test, the null hypothesis is distributed as a student t distribution, not as a Gaussian distribution. It looks like a Gaussian, but it is not a Gaussian. And then the alternative hypothesis has a different distribution. And then we have to find a point such that beyond that point we will reject the null hypothesis. And this point must be such that this area in red must be alpha, that is the confidence level that we want, and this area on the left of the alternative is beta, that is the type 2 error rate that we want. So depending on the particular test that you're doing, for instance, let's say we are doing an ANOVA, and we take the default values. So depending on the statistical test that you use, the distributions can be completely different. So for instance, here you see that it doesn't look as a Gaussian at all. This one either. So that the blue one doesn't look as a Gaussian either. But the principle is the same. You always have to find a threshold such that from that threshold to the right, there is a probability alpha, and from that threshold to the left, there is a probability beta. And all this, the shape of all these curves depends on the statistical test that you are doing. So the main work that you have to do when you calculate the sample size is mapping your problem into one of these known situations. So for instance, this situation with Gaussians was the one that we had when you know the mean and the standard deviation of the observations. And you can go later over the slides and see them with more time. If let's say that I don't know the variance, I have to estimate the variance from the data. This is the most common case. Then instead of having a Gaussian distribution, I will have a t-test, a t distribution. And these t distributions, the shapes will be different. So the shapes of these curves will be different from the Gaussian case. And you had this, for instance, here. You may have noticed that what's this one? This one. You may have noticed that this side of the alternative is not symmetric to the left side. So the right side is not symmetric to the left. It seems to decay more slowly, and I can make it even more pronounced. You see, it decays more slowly. So, and this is not the case for the set. For the set, for instance, generic calculation. So both sides are symmetric. So the most part of your design is identifying which is your case. So I need I need to estimate the variance from the sample, or I don't. Then I will use a t-test or a set test. Or for instance, here you have, let's say, in ANOVA, what you are basing your decision is on something called the F, and this kind of ANOVA tables that you may be familiar with. So the distribution of the F is completely different from a Gaussian. So the sample size calculations for the Gaussian do not apply for ANOVA experiments, for instance. Or for instance, if you move to let me go. For instance, I want to show that my variability is larger than something. So if your hypothesis is on variability, then on the variance, then the shape of the distributions will be completely different again. So your problem really is to map your experimental problem into something that can be calculated. And that is why I think this other program pass is so useful. Let's say that I want to design something based on proportions. So the biggest part of research is done on means. The second biggest part is on proportions. So I want to show that the proportion of animals that have this feature is smaller in this group than in this other group. And then I can go for two independent proportions, test for two proportions, for instance. And then you can say, what are the proportions that you expect in each one of the groups? So this could be the control, for instance, and this could be what you want to detect. So let's say that by default, I don't know, 10% of the animals that are exposed to some substance get some disease. And then you want to show that with your treatment, you protect these animals, and the proportion of animals that get the disease goes down from 10% to 1%. How many animals I need for that? And then again, how you will analyze your data. You will do a normal approximation, or you will do a binomial thing. If you're not sure about what you're doing, for instance, the help of this program is absolutely great. And it has a very, the help is like 1,500 pages or something like that. And then it explains all the details of the design. It gives you the formulas, it gives the design formulas, and it has everything in there. So if you're not sure that you have done the correct mapping, you can always go to the help. And you can also go for examples. So there are examples here. So for instance, here, example 1. So a study is being designed to study the effectiveness of a new treatment. And the standard treatment has enjoyed a 60% of cure rate, and they want to compute whatever. So you can check whether what you are, the test that you, or the sample size formula that you are choosing here. So by choosing a procedure, you are choosing a sample size calculation formula. So you can decide whether it really matches your experimental situation. So whether my problem is really this one. And this is another one. This is the biggest job that you have to do. You have to map, my problem is this, and this is the way to calculate it. You don't need to know the formulas by yourself, but you need to know how to do the mapping. And if you don't know, or you don't feel confident, you may search for advice, and you can talk to statisticians around your lab, your institution, or whatever, and try to explain them what is your problem, and they will try to map your problem into something that can be calculated. I don't know if you have any other question. No?
Hi. I have
Yeah.
one question about the non-parametric tests. I'm wondering if you have a comment on how to exactly know if my data follows the Gaussian curve. I think in biology, many data sets we assume that it follows it without actually knowing if it does or not. Is there a good way of deciphering if that is true or not?
Yeah. You may look for something that are called normality tests. And normality tests, there are a few of them. Like these ones are the ones more known. D'Agostino, for instance, or Kolmogorov, Smirnov, Shapiro-Wilk. And there is a catch in using this test. That is, if you use them with a low number of samples, so let's say I have only 6 samples, so the test will give a p-value that is high. So you cannot reject the hypothesis that the data is Gaussian. But it doesn't mean that the data is Gaussian. It means that there is not enough evidence to show that it is not Gaussian. And so sometimes we tend to use this test, the p-value is high, and we think, oh, my data is Gaussian, I can use all the parametric tools. And it is only that I didn't have enough data. With only 6 samples, the test cannot tell you this is Gaussian or this is not. Right.
So to be sure, you would need at least how much? Like 20 samples? Or I remember something from my statistic basic courses that
typically with 30 it is enough.
Okay.
And otherwise, you can use previous publications. So if someone in your field has taken the time to measure the normality of the things you are kind of looking at, then you can test. So you can use those results. And also, for instance, there are variables that are known to be non-normal. So, for instance, concentrations that you can dilute, like titers, they are not normal. They are normally log normal. Or the number of cells that can replicate and they go several replication cycles, they are also non-normal, or dilutions are not normal.
Okay, I think in many measurements in biology, such testing of normality probably doesn't exist when it goes down to the specifics. So do you think it's an appropriate assumption that it is Gaussian even with lower sample sizes, or is it better to assume that it isn't, in case you won't be able to make so many measurements that you would?
It is safer to say that it isn't. Yeah.
Safer that it isn't.
Yeah. Yeah.
Okay. Thanks.
More questions?
I have a question.
Sure.
Can you comment on performing the normality test on the raw data or your direct measurements versus on the residuals?
Those are different things. So, for instance, let's say that I want to compare two means of two groups, and then I want to check if I can apply a t-test. Then I have to do the normality on the raw data. When you do a regression, one of the assumptions of the regression is that the residuals are normal. And then at the end of the regression process, you should always check that the assumption of normality was satisfied.
So is there any other test apart from the simple t-test where you test the normality of the raw data?
Yeah, for instance, when you are all the tests related to variance that are related to f-test. So at the end, we saw it here. So many tests at the end, they are an f-test, and the f assumes normality too. So the residuals should be, or the data should be Gaussian. And the same for the chi-squared. So all these families of tests, they assume normality, and there are really many.
Okay, thank you.
Yeah. More questions? Otherwise, Rafael, I would like to see the results from the questions. And we have a couple of more questions at the end of this.
Do you see the screen or?
Yeah, we do.
So you can discuss. Carlos,
Okay, so probably you can go to the first question.
Okay. Let me see if I can. Sorry.
Okay, so let's see the first one. So most of you disagree that the sample size imply many animals. That's good. Let's see the next one. Have you ever used the program to calculate the sample size? Now I think you are more convinced that you should at least somehow calculate it in some way. It doesn't mean that it is an absolutely an absolute number, that it is that one and not any other, like what we said at the beginning. it is true that you have not done your experiment, so you don't know. The most important unknown here is what will be the variability of the treatment group, but you have to guess something, because otherwise it is like if you are designing elevators for people, for 10 people, but you don't know at all what is the weight of a person. So if you don't know at all what is the weight of a person, you cannot design an elevator for 10 people. So if you are designing an experiment, you need to assume something of what is the variability of the people, and how do I, how many animals I need to show the effect that I want to show. Yeah. So let's go to the next one. Then, do you feel concerned about the true rates of false positives? Yeah, the first time you're exposed to this is completely shocking, because you're aware that after all your life of experimenting, you might have taken by true effects things that were not really good effects. Okay, let's go next. Well, for this, I will need more time to see what you have written. But yeah, then we can go for the next, the last questions. The last questions, but maybe you can make them, allow them to vote.
Yeah, I think it's possible to vote now, I think.
Okay. So there were a few more questions. One about different allocation sizes that we didn't reach that point. The thing is that if you have a group that is more variable than the other group, so let's say that the treatment is more variable than the control, you don't need to put the same number of animals in the treatment and control. So you can put more animals in the more variable group, and that will make easier the comparison.
You can correct statistically that difference.
Yeah.
Should we go to the next question?
Yeah, let's go to the next one.
I think Carlos is mute his microphone now.
Carlos.
Yeah, sorry. Yeah, so I was saying that the main job is to map your experimental problem into something that can be calculated. These programs, they are great to hide the calculations, but the mapping, it is up to you. You need to do the mapping, and if you don't feel confident in your mapping, try with the help of someone else.
Okay.
And then we can go to the next questions. This was more curiosity that I had. Sorry. Okay, let's go to the next one. So majority of people don't collaborate to design the experiment. And this is more institutional. So many institutions, they don't have this support, the statistical support. And this is something that we should promote, like having some way of getting this help. And yeah, so it is more or less the same to the support to design the experiment and to analyze the data. It is kind of similar.
So there is support probably, but maybe not so easy to find it. That's also a possibility.
That's also, yeah. Yeah.
Okay, so I think that was the last question. Carlos?
Yeah. Is there a last one?
I think that was the last one.
I think that this is the last one, yeah.
Yes.
So, yeah, so I don't know if there are any other comment or anything else that you would like to see.
Is there any final questions or comments for Carlos? It was complex. Some of the things need some digestion, but it was extremely interesting and valuable information that you have shared with us. So thank you very much for it. I give you an applause.
Thank you.
And, so thank you very much. So if there's not any final questions or comments for Carlos, it's 5 minutes over 12 o'clock. Maybe we need to leave it here. We just want to thank you again, Carlos Oscar, and we will share this presentation. We have already done it, but and also the contact details of Carlos Oscar in case you need some additional clarification.
Yeah,
So,
yeah, you may write me anytime.
Yeah, so thank you,
But
Carlos
in
Oscar.
only 3 hours, I had very short time to convey all these ideas.
No, but you gave a very good overview. You gave a very good overview in 3 hours. Hopefully next time you will be able to do it on site at Karolinska. Hopefully in autumn we can do it again with our laptops and we can share information and have more discussion, more interactive. Yes. Okay. But thank you again, Carlos. Thank you all for attending this workshop. And see you next time. Thank you, Carlos, again.
Okay. Bye.
Bye-bye. Bye-bye.